Thank you, Dr. Bassemi, for your great presentation. And now, it's my pleasure to introduce Dr. Fariborz Tehrani, a distinguished professor from California State University, renowned for his research prowess in concrete structures and materials. Dr. Tehrani's dedication to advancing the field has led to groundbreaking discoveries and innovations. We extend our gratitude to Dr. Tehrani for making this journey from afar to share his invaluable insights with us here in Iran. Please put your hands together for Dr. Tehrani.
Good morning. Salam Sobh Bakhair. It's a pleasure to be here. Thank you for the conference leaders, Dr. Khalu, Dr. Zulfaqar Nasser, Ms. Sumay Rezai. Thank you so much for being here. So let's lighten up the mood a little bit with lightweight aggregate. The topic that I'm going to present is about environmental footprint of concrete. I know that all of you love concrete and you're using cement. For every ton of cement, you're introducing 1,040 kilograms of carbon dioxide into the earth. One mature tree would only absorb 24 kilograms of carbon dioxide per year. So next time, you're specifying concrete for every ton of the cement, do calculation and plant trees. That helps you. I'm going to start talking about why is it important, why am I here, why do I advocate for this, and then I'm going to use lightweight aggregate and lightweight concrete as a case study, how we can measure how much damage we are causing, and then how we can address it and mitigate it. The first question comes up is that building on the left that has lasted for 2,000 years, and how come the building on the right has lasted less than 7 years? There is something wrong with the way we are pouring concrete. Recently, I was planning to use a kind of very smart system to magnify this curve, but recently I worked with a couple of great students, and we measured the expected service life of concrete around the world in different climate zones. And none of them, whether they are used in a bridge or a parking garage or a marine system, all exposed concrete. They barely reach the life that we are expecting them to do. Even if you are designing based on ACI 318 or any other similar code. So these are materials and concrete structure built based on the code. And we know that there is a great relationship, very well known, we didn't have to do research to understand this, that as you are increasing the service life, the cost goes down, carbon dioxide goes down, energy consumption goes down, the waste would go down, everything gets better. So it's about me choosing my pair of shoes to go hiking. I'm hearing a lot that we are producing an economic material, cost-effective material. Cost-effective for what? So good luck going to Everest with a sandal. Yeah, you can go there, but you will use 2,000 pairs. Why don't you cough up the money, spend more money, buy a pair of hiking shoes, and you don't have to buy another pair, ever. I've done it. I love my pair of shoes. So what matters is basically life cycle analysis. This is a kind of blown up version. So the other one was global service life. This is just for Iran. I'm here, so I'm respecting what we can do here. And perhaps we have some concrete that would absorb well, let's say in Astara or let's say Bandar Abbas, they are doing a little bit better. But in other places, when you're looking at parking garages, for example, no, the service life is poor. And why does it matter? Well, if you are keep spending your money to repair and maintain what you have, you never have enough money to put on capital expenditure. So there is a paradigm shift, change in سپهر اندیشه مهندسی to stop thinking that sustainability is a conglomerate of different things and you can negotiate between climate and environment and cost and social effect. No, there is a hierarchy. If there is any project that doesn't respect environmental resilience, that project is contributing to the extinction of humanity on the earth, that project shall not exist. Right? You never feed your children with poison because it's cheap. Why would you poison humanity? That's the hierarchy that engineers are after. So first is environment, then social justice, and then building. There are different measures to do so. There are pyramid of need. There is a net zero system by EPA. There are United Nations sustainability goals. So we can go with all of them, and they are practically very similar. But what we are going to do is an objective measure. There are different standards. In Iran, we do have service apps, which is resembling US Green Building Code. But I'm going to use, and maybe the only one that's kind of mandatory, is ASC Standard 73, which was just published a couple of months ago. But we don't have any kind of requirement for this, so we have to understand that. But how do we do the job? Well, we do life cycle assessment. Right now, there are environmental product declarations. There are labels, environmental labels, the same way that you buy like a carton of milk, and then it says how much calcium, how much vitamin it has. It would tell you the material that you're using, how much energy has been consumed to produce this, how much carbon dioxide it has had. So basically, you understand what's the damage. Most producers are doing something that we call cradle to gate. Like a cement plant would say, I know where my material come from. This is the amount of energy. This is my bill of energy. And this is what happens when I'm bagging the cement and selling to you. But what happened to that cement, we don't know. We do understand that we have to go all the way from cradle to grave. That means I need to know what's going to happen to the material when I'm putting in construction, what happens in the use, what happens when I'm decommissioning, deconstructing the structure. I put it into recycle facilities. And what happens after that? Some material, long after you have used them and recycled them, they are still polluting the earth. So that's basically a bottom-up estimation of what we're going to do. The example I mentioned is Lifecycle aggregate. Why is it important? Other than that, I'm the director of ESCSI. Well, it's important because when we are producing Lifecycle aggregate, we also produce carbon dioxide. It's not as bad as cement. It's about 100-something kilogram, not 1,000. But still, does it make sense to produce this type of aggregate? And they are available around the world. The top one is the one that you see in Iran. Similar one in Italy, Netherlands, a bunch of Europe. And the bottom one, expanded shale, that we have United States, Northern America, basically. The material is basically a porous structure. So when you buy Lifecycle aggregate, you buy air. So there is a porosity inside, and that porosity creates a moisture dynamic that's applicable in different applications, like internal curing of concrete. You're trying to create thermal insulation when you just want to put it in your plant to make sure when you're going for vacation, the plant doesn't die from lack of water. So you don't have to water the plant every day. So different application, but this ceramic is morph. Am I correct? I learned this from you. So this plant is morph, somewhere between a mineral and a crystallized version, right? So my thank you to Dr. Nawat Molen for teaching me this. We have, again, done similar things. So we do have good experimental evidence in a report that I published in 2020 that adding lightweight aggregate to concrete does a couple of things. Reduces the density. Well, we knew that is light. Number two, that many people don't know, it increases the strength. The strength of lightweight concrete is more than the strength of normal weight concrete. And number three, the service life of any sort of lightweight concrete, whether you add coarse aggregate or fine aggregate or a portion of any of them, is more than the normal weight aggregate. There is nothing normal about normal weight aggregate, except the name, right? Maybe we have to change it. How did we approach the problem? This is basically the setup for the whole process. We start measuring how much energy do we need for a loader or dozer to excavate clay from the earth, bring it to the factory, burn it, heat it up. If you don't know, it's basically heating up the clay for, or shale or slate for 1,000 degrees centigrade, and then cooling that down fast. How much energy goes to gradation, packing, sending to the construction, going to the construction, at the second column from the left, putting that into use all the way to the bottom. That's a really, really cradle to grave. The work that has been started like a couple of years back with good students. The first one is from Tehran Polytechnic, second one from Arab University, third one I do myself. And then we have the report that's basically coming up very soon. If you compare with the rest of the world, I mean, there are different type of material mentioned that practically everything is based on tonnage, right? It's weight-based material. Remember, the mass doesn't diminish, doesn't get created. So we can create the flow of the mass and see how much do we need. And the more you expand the material, per cubic meter, per volume footprint would go down. That's the whole idea. Let's say you want a cubic meter of sand. How much cubic meter do you need to excavate from the earth? 1. How much do you need for expanded clay? 1/3. Why? Well, because we expanded. So mining goes down. So the amount of energy and emission are kind of commensurate with the expansion rate that you need to get. And there is also an ugly fact that you cannot use solar power to heat up a kiln, cement kiln or lightweight. So these are heavy duty. I wish at some point we can create some solar panel. We cannot do that. So most of the energy that's being used is non-renewable primary fossil fuel. That's the ugly truth about cement and any gypsum or any other factory that we have. And each one of them does have a little bit effect on emission, for example. You may not imagine, but electricity is the worst. How come? Because the power plant that gives you electricity, guess what? Is burning fossil fuel too. And waste some of it on the way to the plant. So things are a little bit not as always appears. On transportation, well, you know that if the load on a truck is lighter, you spend less energy, less fuel. It's no brainer, right? As you have all, everybody knows this. You lighten up the load on the truck, you reduce energy and emissions. When you're getting to assembly and construction, no, it's not just concrete. It's not just the aggregate. It's a steel structure material, something. You have to add up everything else, all the saving that you have. So I'm going to give you 3 case studies. Case study number 1. Something that most people know. So what would happen if you replace normal weight concrete with lightweight concrete on slab, like composite slab on a building, done very differently. There has been like a proposed study. It was done by Walter P. Moore. So they did the structural design. So I'm borrowing a lot of their material and I just convert it to environmental footprint. They consider 3 different case studies. The bottom one is the normal weight, which is not normal. And we are reducing the weight from 2300 to 1840, right? So what happened? At the bottom, of course, you see the color coding, and you are looking at the amount of the material that you are going to use for this concrete. Remember, if your slabs are lighter, you are going to need less skeleton, less footing, less column, less everything, right? So the consumption of the material would go low. How about construction? Well, if you have less steel material, you need less crane time. The crane also burns fossil fuel, by the way. So you're, again, saving. So this is our energy calculation. Our energy calculation basically shows that, maybe because this is the first one I would explain, A1 to A3 is production. A4 is transportation to the site. A5 is construction. B1 to B7 is the use. C1, C4, deconstruction, demolish, haul it, go to the recycling plant. D, what do you do with the leftover? So this is the amount of energy. Even in the D, you have to spend energy. You have broken concrete. You want to convert it to aggregate. You need a crusher. Guess what? That crusher needs diesel fuel. You're still polluting the air to recycle concrete. So that basically gives me something that I have to say right now. All those people who say net zero, zero doesn't exist. You cannot have zero energy. If I produce a material and I burn the material to extract the same material, I'm not going to get the same. همه میدونن. همه. It's impossible. Net zero doesn't exist. But in comparison, we can do something better. So now I'm comparing those three scenarios the structural engineer gave us, Walter Fillmore designers, with conventional or normal weight concrete. You can look at, we are reducing carbon dioxide, we are reducing energy, emissions, waste, and water. All of them are down. Another example are masonry systems. Most in buildings that are non-engineered, they are using at least some sort of masonry units for them. And they are light, again, and they provide thermal insulation. What happens to them? According to the chapter 19 of Iranian National Code, you can basically categorize, classify different kind of units, those that are meeting certain amount of thermal insulation conductivity. So I've kind of created class 1, 2, 3 based on the chapter 19. Special class is the super thermally insulated material. They go above and beyond the code. And then I have some that I call it none. None means they're like partitions. They are not meant for exterior wall. So the Iranian National Code doesn't allow them to be considered as thermally insulated material. So we went, again, the great paper by Dr. Sadiqi that I borrowed in this project. So we went through around Iran and calculated number of degree days for heating and cooling. So let's say the temperature is supposed to be 25. So every hour that the temperature outside goes more than 25, you need to cool this down, or goes under, you have to heat it up. We calculate for all cities. We can take average or we can go locally, doesn't matter. Also, we would calculate how much, again, energy emission goes to construction of the material. Which one is safer? Lifting heavier stuff or lifting lighter stuff? I don't have to answer you. So there are some side effects, good side effects, that we are not considering. But right now we are just crunching numbers. What's the source for this number? Cost analysis. In Iran, we have a contractor syndicate, سندیکای پیمانکاران شرکت‌های ساختمانی. We have done this since I was a student, even before I became civil engineering student. Then we can go around the different classes and different climate zones, right? So I can talk about what would happen if you use block number 3 in Abada. How about if you put block number 7 in Astra? It's computer. We have pages and pages of this calculation. Here I'm just showing you average values, but I think an engineer, the engineer of the record shall calculate this for her own project in every location. This is a summary of calculation. Again, you are looking at the values, and this is maybe the major one. Again, on the left, you can see that there is no zero. You keep calculating again, spending energy and emissions. But on the right, you can see how superclass, class 1, class 2 and 3, and normal weight wall behave. So it is true. Maybe for certain amount of aggregate, you need to spend 1 kilowatt of energy to produce it. Throughout the life cycle of the building, you save 1 magnitude of order higher than that, 10 times saving. Now think about those people who produce material that's cost effective at the time of production. They are betraying the industry. They give you something that saves you cost now, they charge you 10 times later. Right? There should be something like a criminal charge for this. 12. Third one, things get better. Now we are talking about internal curing. What's internal curing? Well, you know what the curing. You combine cement and water, and for the given volumes of those materials, the volume of hardened cement is 6%, 7%, 8% less than the total volume of water and cement. So concrete shrinks. And to compensate, and if you don't compensate that, it's going to crack. To compensate, you add water. How do you add water? According to the standard, We have all done it in our technology beton in academia. You submerge concrete into the water. Perfect, done. We did it. I got A from Dr. Khalu. Perfect. Can you put a dam underwater, submerge it to cure it? How about road? How about retaining wall? How about buildings? No, you put some sort of material, like burlap, for example. You put moist burlap under that. I can give you evidences. That water would barely travel into the concrete more than 2 centimeters. So if you have 4 centimeter concrete, good luck. The bottom is going to desiccate. So that curing is now in ACI, American Concrete Institute, is called, that was my time. And I'm going to be done in time. That is now called external curing, not curing. It's good. You should not throw it out. It's good. It helps the finishing of the concrete. It preserves the surface of the concrete. It does not cure the body of the concrete. So what do? We put fine, lightweight aggregate that can absorb up to 15% of their weight moisture. We submerge them for 72 hours to make sure the water goes in. We replace certain amount of the sand that can be calculated with that value, with that lightweight aggregate. So when the cement wants to get cured, there is a fine lightweight aggregate next to the cement within that 2 centimeter region. So we hydrate the concrete from inside out. Result, strength goes up again. Please never ever tell anyone that lightweight aggregate has less strength than normal weight. Please don't. The strength goes up. Service life goes up. How come? You have more hydration. You have no crack. This one zero works. There is zero cracking, and there would be no penetration of chloride ions into the concrete ever. Done. So consider slab for like a roadway, right? We are talking more like exposed concrete, right? Roadway, because that's the type of concrete that would be exposed to corrosive material. That's done in, this is Fahab Beton's lab at the bottom, and top one is my own lab. So thank you, Fahab Beton, for helping us with the project, and the paper is published already. But basically, we are changing the transport properties of concrete. So this is, again, this result, you can find it in my 2020 report. Well, I talked about internal curing. That's internal curing. The strength goes up. I've already talked about that. There are other advantages too. Let's say on a roadway, what will the spacing between your joints? Depends how much cracking you expect. If you don't expect any cracking, well, you can increase the spacing. There are minor advantages as well. And after doing all number crunching, we get to this. So you can reduce the cement. If the strength of concrete is going to go higher, well, you can reduce the amount of cement, 50 kilogram per cubic meter. Why not? Number two, you say, no, I want to keep the cement. That's fine. Reduce the thickness of the slab. Either way.
Dr. Tehrani, only 2 minutes, thank you.
Of course. This is the reduction, emission, energy, water, and waste. On that one. So let's compare everything together. The more sophisticated you get, the more saving you are going to have. You are counting only on lightweight concrete because it's light. The gray one gives you the saving. You get smarter, you calculate thermal insulation, you can save more. You get smarter, you hydrate cement with lightweight aggregate. It even goes higher. There is no conclusion. That's it. So it's a life cycle analysis that would allow us to see really what's happening. Never ever buy a sandal in a hiking shoe store. Never ever buy cheap cement or cheap aggregate. We have to always look for the life cycle. Bunch of reading. I can come back to this if you want to scan all the QR codes. Spent good amount of time. I didn't know we can copy QR codes. I learned something. And a big thank you for Lico Company for sponsoring the project. And even bigger thank you for all those students you see their names on the right. I barely did anything. It's all my students. Thank you so much.
Thank you. Thank you very much for your nice presentation. Only one question, please. Yes?
Thank you very much for your informative presentation.
Sure. Thank you.
My question is about the relationship between the compressive strength and density of the concrete made by lightweight aggregates. Normally, lightweight aggregates has less strength by itself, so there should be an optimal density. For example, in my experience, when the density goes down up to 1800s or so, yes, the strength wouldn't be affected that much. But do you have any data or mixed design relating to the
Sure.
strength? You mentioned that it increases the strength.
Yes.
How so?
We have two different classes of lightweight concrete. There is insulative lightweight concrete. There is structural lightweight concrete. The insulative definitely has less strength. It's not designed to be structural. So that's totally put it away. When you are using internal curing, you're only replacing a third of the sand with fine lightweight aggregate. There is no change in the strength. There is better hydration, the strength goes up. Again, so we have no problem with that one. Your question applies practically to coarse lightweight aggregate concrete. And there is a limit. So I would never say that you can reach lightweight concrete to 12,000 psi. Never. But 6,000, that's the standard practice. Practically, one of the problems that I have in my research is that when I ask plants to feed me with their concrete, they say, sorry, we only have high strength lightweight concrete. We do not produce normal strength lightweight concrete. Nobody buys that. Everybody wants high strength. So they go with lightweight concrete. And then how do you meet this? I'm so glad Dr. Tasuji is not here to criticize me. Additives, water reducent, all those new stuff that's coming. So that's the magic of chemical things. So basically what happens is that the crushing strength of the aggregate has the least amount of effect on the overall strength of the concrete. That's how they make it. But you have a point. There is a limit. 12,000 doesn't exist. The maximum we have received is 8,000 psi. 56 megapascal? Something in that level. One question that you didn't ask, sorry, you said one question, so I'm amending his question. How about tensile strengths? As a member of American Concrete Institute Committee 213 was updated the new code, the lambda value in ACI 318 is simplistic and super conservative. I do not agree with that. Actually, a good student of mine has already published 2 other papers in the same conference. You can find it. And we are showing there that in ACI 318, they say use this for lightweight concrete. There is a difference between different type of concrete. You cannot use the lambda for expanded shale clay slate as the same as slag, or as the same as expanded fly ash, or pumice, or God forbid if anybody uses scoria, please don't, for scoria. So there are differences, and ACI 318 is blind to the source of aggregate, and that has caused a problem. ASHTO has already started claiming that lambda values are not correct, so the new ASHTO is out, they have new data. What we did, we went one step above the ASHTO, and we discriminated between different type of aggregate, and we showed that if there is going to be a lambda value, it cannot be one number for all of them. So that would also help us a lot with people who are dealing with bonding and tensile strength, shear strength that are super important. Sure. Thank you. Thank you so much for sharing this session.
I think it's true just for low water cement ratio, in fact. I mean, outage shearing cage or internal curing is necessary just for low water cement ratio, but less than 0.5, 0.4, something like this. Normally, in our concrete, the water cement ratio is high. It's higher than, I mean, normally don't need to internal curing for the most used concrete. Somehow, for example, for pavement.
You have a point to the fact that, if you don't mind, I'm going to repeat this basically in my own wording, that as the water to cementitious material ratio goes down, you're going to expect more shrinkage, more early age shrinkage. So shrinkage becomes more problematic. Therefore, internal curing is going to contribute more to predicting that. But look at any foundation with 3,000 psi concrete that's placed every day, anywhere. They all crack. Is
But
that a problem?
Not exactly because of the oxygen shrinkage. Maybe
We are talking about cracks that you
of
cannot
another
see. And you know, how do we measure service life of
because by
concrete?
measuring, if you measure the oxygen shrinkage and chemical shrinkage for high water cement ratio, it's not a lot. I mean, it's limited. Well, anyway.
I
And
do
another
agree.
thing.
It has less effect.
Oh, okay.
But what would you say about desiccation of cement? Anyway, cement needs water to hydrate. And if there is not enough water, it's not going to hydrate. So we lose cement.
In terms of
In
hydration,
old time, they used to tell us that concrete keeps gaining strength over years, right?
No,
Why?
I would
Because
say just
not all the
you
cement has
don't-
been hydrated.
you don't propose lightweight aggregate for internal curing for all concrete. You don't
Yes,
want
I
to
do.
say that.
Yes, I do.
You make,
Any concrete that's exposed to harsh weather or harsh climate, any concrete that's susceptible to corrosion, yes, I do.
I don't
But
agree with you.
if it's like a skeleton, like a covered, well protected, if service life doesn't matter, no. That's what my example was, like bridge decks, marine, parking garages, a balcony in close to salty air that's coming. If it's susceptible to corrosion, yes, I do.
Okay, we can talk.
Sure.
Next, another thing. If you introduce seismic issue, because lightweight aggregate structural concrete can reduce the shear force, so it would be better. I mean, seismic issue can be interesting also for service life.
Correct.
It's just a comment.
Correct. So lightweight also helps with the inertia. Well, like at least in
Because
my
you
market,
talk about service life,
like in
and
United
during the
States.
life of
Correct. In United
Iran, in
States,
fact,
they would call me selfish if I talk about seismic because it only happens in California. The rest of the state is pretty much. But you have a point. Yes. I mean, seismic is something.
Thank
that
you
we
so
would know.
much.
Of course.
Upload again,
anytime.
please. Thank you.
Thank you.
Dr. Tehrani.
Thank you.
Thanks for very nice
Of course.
presentation. In the first or third or second page, you show me that you have used it in garage and parking. Did you test it of the crushing and abrasion and compare with a normal concrete?
Not in this research, but we have done abrasion resistant for other purposes. So we have papers, I can send it to you, on floor finishing, because most of the abrasion issues has something to do with the screeding and the abrasion and the floor finishing practices. And for that reason, I love external curing, because external curing would give you exactly what you want to finish the material properly. So if you test lighted aggregate, let's say using a Los Angeles test, you might be surprised at that saying that you get a little bit more crushing in that Los Angeles test. But now in transportation, we basically either don't use the Los Angeles test or we correlate the material with other version, like the jigsaw abrasion test. Because the reality, when you have like truck traffic on roadway, what happens on that one, it's totally different from Los Angeles test. So it's not what crushing, it's what abrasion, as you said, truly. Maybe I can give you an anecdote. Our aggregate is qualified for high friction surfaces for chip seal. It's approved. So it's one of the things that create additional surfaces. And the reason for that is that because of the porosity, we never, think about decorative stones. They're highly polished, everything is beautiful. This lightweight aggregate is porous. It has a lot of holes. You cut it, you get a lot of roughness. That gives you enough friction for roadways and those stuff. When it comes to abrasion, but the reality is that you have concrete cover. If your concrete cover is well cured, well finished, right after placing the concrete, you never reach the surface of the aggregate. So you are pretty much safe. But you said it that that's a, thank you for being that, that's a kind of a parameter in designing roads, definitely.
Thank you.
Of course.
We thank Dr. Tehrani for his great presentation. It was immaculate. And now,